27.37. A thin, 50 centimeter long metal bar with mass 750 grams rests on but is not attached to two metallic supports in a uniform 0.450 Tesla magnetic field, as shown in this beautiful rendition here. Part A. A battery and a 25 ohm resistor in series are connected to the supports. These guys. A battery, wow, can't read today. A. What is the highest voltage the battery can have without breaking the circuit at the supports? So, we have a battery, we have a resistor. This is going to start pulling some current through here. Current, yay, yay, yay. So our conventional current comes out of our plus and is going to go through there and carry on its merry way. So if we have a current in a magnetic field, it's going to feel a force. According to IL cross B. So just like force on a charge is QV cross B, force on a current is IL cross B. So if we take our right hand rule, first vector is our IL, that's our pointer finger. It's going this way. Second vector is our B, that's our middle finger. It's going into the page because it's arrows. And our resultant is our force, so that's pointing up. So our wire here is going to feel a force pushing it up off of those supports. So it's going to go whoop. So in order for that to not happen, the weight of the bar has to be greater than the force that the field is trying to push it with. So the weight of our bar is mg, and the moment when that force is going to overtake it is when those are equal. So in this case, our IL is perpendicular to B because we're going left to right, and then our B is going into the page. So we can just write this as ILB. Cross product goes away. So the current that this is going to take is going to be mg over lb, where m is 750 grams, which is 0.750 kilograms. G is 9.81 meters per second squared. The length of my wire is 50 centimeters, so 0.5 meters. And my magnetic field is 0.45 Tesla. So the current, the maximum current through this bar that we can have before it starts to hop away, 9.81, is going to be 32.7 amps. Holy crap, that's a big current. Fun fact, 1 amp is enough to stop your heart. So don't touch this. Alright, so that's how much current it's going to take. And now we can use Ohm's law to figure out what that voltage is going to be. So this is still just a wire. This is not a resistor. I just drew it fat so you could see it. So from Ohm's law, V equals IR, the current is going to be 3.27 amps, and our resistor is 25 ohms. So the maximum voltage that this circuit can have before that wire is going to start moving upwards in the direction of the force is 817.5 volts. Alright, so part B, the battery voltage has the maximum value calculated in part A. If the resistor suddenly gets partially short-circuited, decreasing its resistance to 2 ohms, find the initial acceleration of the bar. Okay, so now we have the same voltage, but our resistance is changing. So our current is going to change to reflect that. So our current is V over R. So our V is 817.5 volts, and our resistance is 2 ohms. So that's going to be holy bejesus amount of current. Right? So that's our holy bejesus amount of current. So if we look at our free body diagram, we've got our weight pulling us down, our force from the field pushing us up. So we have QV, that's not the one I want, IL, B pushing up, minus mg pulling down, is equal to ma. So now this guy is going to be accelerating because his current is way above the maximum current. So he's going to go floop right off the thing. Alright, so if I plug these in, well, first I'm going to divide by m. So my acceleration is going to be I, which is 408.75, L, which is 0.5 meters, B, which is 0.45 Tesla, over the mass, which is 0.75 kilograms, minus G, 9.81 meters per second squared. Alright, times 0.5 times 0.45 divided by 0.75 equals that. Minus 9.81. It's going to be 112.815 meters per second squared. So this thing is just going to go right off. Right on off.